So 6.2, I would hope that you would agree with me that that was it's a lot of material. Yeah. And 6.3 is the same way. It's going to take us 2 days to get through this section. But the good news is after this, you know, it eases up a little bit. Okay, so for maybe a day, for like a day, for one class period, it'll ease up. Yeah.
It's super easy because we learn like so many things.
Yeah.
And then it's like, oh, look.
Yeah. Yeah, so we're going to have to, yeah. So, okay. So you all ready? We kind of need to kind of take a deep breath, get ready for some new stuff, all right? All right, so the first part of this, you know how the last section was broken into 2 different topics and we did it in 2 different days? This is going to be kind of like that, except that the first today, it's not a separate topic. We're just going to review some things that we should know how to do now, all right? And everything that we review, we're going to need when we get to the problems. So the first part here is not the problems from the section yet, all right? So first, some preliminary stuff. There is a formula number 17, that says that if you have the integral of 1 over u squared plus a squared du, that the antiderivative is this. Now, you'll recall this formula that I told you all to memorize that, get used to seeing it, right? That the antiderivative of this is arctan of x, right? Well, what happens if we replace that 1 with any number, like 9 or something like that? The antiderivative of this is not arctangent of 1 over x squared. It's not arctangent of x. Okay, the antiderivative of this is not. It's only if that was a 1. So this formula generalizes it a little bit more. Imagine that that was x here and that's x here. It says, look, if you've got an a squared here, right? So let's go back to 9. Then a is what? 3. Then the antiderivative of this would be 1 over a, so 1/3 arctangent of the variable x over a plus c. Okay? So we just need to account for that now. Make sure that if this number is something other than 1, we take the square root of it and then we put it here and here. Understand? Okay. Now, this formula, guess where you can get this formula from? If no one had ever told you about this formula, the way you could get it is you could rewrite this problem as the square root of that squared. Okay? That's the same thing as x squared plus 9? Yeah. All right? And then you could use trigonometric substitution. That's what we did last class, right? And if you do that, you would get this at the end. So this formula actually comes from doing trigonometric substitution on this. We're not going to do it, but that's where it would come from. All right? So that's formula 17 on your formula sheets. Moving on. I have now a list of 8 integrals. Here are some integrals we should be able to handle right now, today. Let's confirm. All right? So I'm going to go through these 8 integrals right now and make sure that we know how to do them. And you're going to see that I'm going to be showing you some new techniques today for these 8 problems that we haven't done. All right? But they're going to extend on what we already know. So let's start with this first one. Anytime we see an integral where we have a constant, yes, 2, over a linear function of x. So that's a linear function of x. Then we could always do this. We could always let u be x minus 4. So we could let u be the denominator. The derivative of, so I'm doing a basic substitution. Du here would be what? What's that? Dx, 1 dx. And then you could rewrite the problem. So if I rewrite this problem, how about that 2 up top? Can I just pop it out? 2, 1 over, and then what's here? U, and then dx is du. And so this just becomes what? 2 ln absolute value of u plus c. So this is just 2 natural log of x minus 4 plus c. Right? A real quick basic substitution first turns it into something pretty simple, and we're here. Good? Okay. Let's look at something else. Here's another one where we have a constant over a linear function. So this is exactly like the previous problem, right? Exactly like the previous problem. But we're going to have something different happen. Because when we let u be 4 minus 5x, the derivative of that is not 1, right? It's negative 5 dx. And I don't have a negative 5, so this is where I'd have to scale both sides. So I'd have to divide both sides by negative 5. Negative 1/5 du equals dx. Is that all right? And then we rewrite the problem. So this becomes integral 1 over what? U. And then dx gets rewritten with this. So I'll have a negative 1/5 out here, and then du. And the antiderivative of that is natural log again, right? So this will be equal to negative 1/5 natural log of the absolute value of 4 minus 5x plus c. Questions? If these seem easy, good, because they're supposed to seem somewhat easy compared to what we've been doing. Are we happy with that? Okay, so I want to go back up to number 1. I just want to kind of point something out. Back on number 1, if we were to have pulled the 2 out, I would have had 1 over x minus 4, right? Yeah. dx. So when I see a constant like 1 over a linear function, I know the antiderivative is going to have the natural log, okay, because that's like a 1 over u. The only question is whether or not I'm going to have to scale anything out. And if you look at this, our x had a 1, so I know dx is going to be 1, right? So I don't have to scale anything. If we go back to the second problem, here I have 1 over a linear function, right? And I know the antiderivative of this is going to be natural log of it. But I'm going to have to scale it by negative 1/5 to kill off that negative 5x, right? So in general, not in general, let me give you one more example. Let's do this without doing a substitution. 3 over 4x plus 1 dx. We want to be able to do that without doing any substitution written down. Just write the answer down. That's where we want to be. So we see we have a constant over a linear. The constant could come out, right? So we get 3 comes out. Then we know it's going to be 1 over u, so we're going to get a natural log of the denominator. But I'm going to have to scale this by what? 1 over 4. So 1/4 out here like that. Okay? So we want to be able to do these problems without actually doing the substitution. Although you can, it's just, again, you're taking a test, right? And if you have like 3 or 4 of these show up, you don't want to be taking the extra minute for each one to try and do this, right? It should be almost automatic from here to here. So yes, you could turn that into 3/4 and we're done.
So what problem is that, or you just made it up?
I just made it up. Yeah. Now, if you like general formulas, which some people do, we could actually create our own formula here if we wanted to. We could say anytime we have 1 over some linear function of x, ax plus b dx, right? That I know the antiderivative of that's going to be natural log of ax plus b, right? Plus some constant, but I'm always going to have to scale out by what? 1 over a, right? So I'm going to have to put a 1 over a. Doesn't that look familiar? Didn't we do that with sine and cosine? It's the same exact concept. We have a linear expression down here. We know the antiderivative is natural log. 1 over u is the antiderivative is natural log of u. But we have to compensate for that chain rule that a is going to pop out when we take its derivative, so we kill it off with the 1 over a.
It only works when it's linear.
It only works when it's linear down there, yes. All right. All right. I'm recording. So look, we've already finished 2 of 8. Awesome. All right, what if we have a constant over a repeated linear factor? Repeated linear factor. So this is now we have something different, don't we? All right, it's repeated, which means that it's a linear factor, but it's squared, right? So the antiderivative is not natural log anymore. Natural log only works when you have 1 over u, right? 1 over u squared doesn't work, right? But we could make a substitution, again, of the linear function, which would be 2x plus 1. The derivative of that would be 2dx. I don't have 2dx, so I have to scale it out, 1/2 on each side. And then what would that integral become? 1 over u squared, and then 1/2 outside, and then du. And that's the same as u to the negative 2, isn't it? So I'm going to have to use power rule. Look, it happens a lot. People will take the antiderivative of that and they'll say natural log. Okay? It's only when it's 1 over u, right? Not 1 over u squared. So this one we have to use power rule. So I just rewrote it and now I use the power rule. So when I do that, I'm going to get negative 1/2 u to the negative 1 plus c. I hope you agree. Yes? And then negative 1/2, and then u, what was u? 2x plus 1 to the negative 1 plus c. You could leave it like that. If you wanted to, you could write it like negative 1 over 2x plus 1, like that. Like you could decide to go ahead and drop that down with the 2. If you wanted, you could pass the 2 through and make it 4x minus 2. It's up to you. Any of these are acceptable answers. All right? Is that all right? Do you see that we still, because it was linear here, even though it was repeated, do you still see that we still had to scale out the 1/2? It was just that the antiderivative wasn't natural log anymore. It was, you know, this negative u to the negative 1. So let me give you another one. Let's see if we can do it without doing any work. Okay? 1 over 5 minus x. I forgot to square it. Squared. All right. What am I going to have to scale it by? Negative 1, right? Because I have a negative 1 here. And so it's really 1 over negative 1, but that's the same thing as negative 1. So I'm going to need a negative 1 out front. And I realized that this is really going to turn into like 1 over u squared, which is really u to the negative 2. And the antiderivative of u to the negative 2 is negative u to the negative 1. So I have another negative u, right? Negative u, what's u? 5 minus x to the negative 1 plus c. Now, if this is stretching too far for you to go from here to here, it's okay. I'm just telling you, you want to try and get to here at some point. If you need to make the substitution and do it, fine, but the standards, I guess, for this class is that you can eventually, meaning by the time we take the next exam, be able to do this one mentally.
So can you just go over the process again, that one, if you don't mind?
Okay, I see that it's a linear expression that's repeated. So I know that the negative 1 has to be compensated for. When I take the derivative of this, right? I'm going to have a negative 1 pop out, and I don't want that negative 1, so I have to divide by negative 1. That's this step right here. I know I'm going to get a negative dx, so I divide both sides by negative 1. So that's that, right? Okay, then I realize that this really is going to turn in, that's really going to be like 1 over u squared, which is really u to the negative 2. And when I take the antiderivative of this, the antiderivative of that is negative u to the negative 1. I'm just using power rule there. And that's this part, negative u to the negative 1. Are you just being agreeable, or you understand?
No, yeah, 1 over negative 1.
Uh-huh.
That's negative, and then you substitute that for u.
That's right.
Then, yeah.
Yep. And so this actually could turn into just 1 over 5 minus x, right? Because the negative and negative become positive. And so that to the negative 1 is that. So if we take derivative of that, we should get that right there. Okay, something to work on. Something to work on to get to the point where you feel real comfortable doing that. Now, would you like to know why? I mean, why we need to do this faster? We're going to be doing problems. I didn't even let you answer. We're going to be doing problems that are going to look really complicated, and what we're going to be trying to do is break it up. Okay, it's like we have this big monster problem, and then what we do is we split it up into separate problems, and each of these separate problems is going to turn out to look like one of these 8 things I'm going to show you. So you'll be able to do each one individually. All right? And the breaking up of the big problem is called partial fraction decomposition. We're not doing that yet. We're going to do it. We'll probably get to it a little bit today. Okay, here we go.
I'm sorry, I'm with you.
Another one. Ooh, so look, is this any different than the one before? A little bit, right? A little bit. It's just that it's cubed instead, right? It's cubed instead. So let's see if we can think through this without actually doing a U substitution. First, am I going to have to scale anything out? No, because I have a 1 here, right? So the derivative of that is going to be 1, so I don't have to scale it out. Now, that means that this is really going to look like 1 over u cubed, right? Which is really u to the negative 3. What would the antiderivative of u to the negative 3 be? Negative 1/2 u to the negative 2. That's the antiderivative of u to the negative 3. Isn't it?
Yes. Then plus C.
Plus c. And I shouldn't have even put u there, but u is going to turn out to be x minus 5, right? The antiderivative of 1 over x plus 5, that quantity cubed, is going to be negative 1/2 times x minus 5 to the negative 2. And we could check it real quick, right? Take the derivative, negative 2 comes out, hits that, becomes a 1. Right? Subtract 1 from the power. It's this to the negative 3, right? And then take derivative what's inside. 1, and that's that, right? So it looks like a constant over a linear expression. You might have to scale, but that's going to become a natural log. Constant over a linear, that one you'd have to scale it by negative 1/5. This one, you have to scale it by 1/2, but then you also have to take the antiderivative of something like u to the negative 2. This one, no scaling involved because the coefficient on x is 1, and you're taking the antiderivative of something like u to the negative 3. And you can imagine that if I change this number to the 5th power, then it would be the same process, wouldn't it? Okay. So now let's shift gears. What if we have a constant over a quadratic expression that has no x term in it? What I mean by no x term is it has an x squared term, it has a constant term, but there's no x term. Like we don't have an x term. We just have the squared term and a constant term, right? So how could we go about doing this? That would be a trig substitution problem, yes. But because it looks exactly like x squared plus a squared, that's formula number 17 that we started class with, right? So this, we go right to the formula. Nothing else to do. A here is what? 3. So this is 1/3 arctangent of x over 3 plus c. All right? That's it.
Whenever we do it, we gotta take formulas 17.
Well, I would like that, but if you get it, I'd be happy to. All right, so how about this? I mean, if you go right to it, I'm kind of going to know you used the formula. I don't know who said that, but okay.
You don't have like a nice number.
Yeah, so what about this?
It's just 1 over the square root of 3.
Yeah, we have to look at 3 as being root 3 squared. Right? So I can go straight to the formula on this one. This is 1 over root 3. arctangent of x over root 3 plus c, and I'm done. Yes? Okay, so doesn't this look, well, this one, why was this 3? Let me ask you that. Why was this 3? Because we're looking at that number as being a squared, right? Right? So what do you do to get 3? You took the square root of 9, didn't you? Square root of 9 is 3. But here, this number doesn't look like something squared, but it actually is. It's root 3 squared, right? And so a is root 3. Got it? Okay, so if we have a quadratic with no x term, we look pretty good. Do I have one with a minus in here? Oh, I don't have one with a minus, so let's do one with a minus. Let's do the same problem with a minus, because that does not look like the formula that we just worked with, number 17. Right? That's not formula 17. It has to be a plus. Do you have a formula on your formula sheet that deals with this? So let's look at our formula sheets. Number 17, I'm looking at reference page 6. Reference page 6 is allowed on the test, and formula 17 is the one we used before, but if you look at formula 20, it says integral du over u squared minus a squared. Oh, shoot, no, I'm looking at the wrong thing, sorry. Right? Hold on. Oh, I am right, never mind. Equals 1 over 2a natural log of u minus a over u plus a plus c. That's formula number 20. Now, the variable in this formula is u, right? So u is like the x. Also, do you see how in the book they put the du on top here instead of the du out to the side? It's the same thing, right? Okay. So can I use that formula? Yeah, I can use it. So it'll be 1 over 2 times 3, so 1 over 6, natural log of x, right? X minus 3 over x plus 3 plus c. So this would be 1 over 2 times 3, natural log of x minus 3 over x plus 3 plus c, by formula number 20. Where do you think the formula came from? I'll tell you where it came from. All they did is they looked at this as being the square root of that squared. And then they used the trig sub. And they did trig sub, and they came up with a formula. All right? The moral of the story is this. If you have a constant over a quadratic and you don't have an x term in there, you're going to go to a formula. All right?
So wasn't the answer 1/3 tangent?
That's when it was plus. I changed it to minus.
Oh, is it a new problem?
Yep, I did a new problem. I'm going to do another new problem. You ready? Here it comes. What happens if I change this to 9 minus x squared instead? There is formula 19, isn't there? However, I understand it's formula 19, but I want you to also understand that what you could do is still use formula 20, but just pull a -1 out. So imagine if I factor a -1 out of the bottom, right? Wouldn't that change the bottom to -9 plus x squared? Like that? Wouldn't that do that? And then that right there is really that, and that's a problem we just did before, right? So all it would do in terms of our answer, what would it have done to change our answer? It'd be negative 1 over 6 natural log of x plus or minus. What was it on formula 20? Minus 3 over x plus 3 plus c. So do you see what I'm doing here? Here's the original problem, right? I take the negative out, and then it looks like the old problem, but I have to throw -1 in it, right? Now check this out. What would you have gotten if you would have used formula 19? If you said, you know what, I don't, screw him, I'm going to use formula 19. I'm not pulling the -1 out. What would you have gotten according to the formula? 1 over 2a, so you'd still get 1 over 6, natural log, and you said what? These two are flipped, aren't they? So it would be x plus 3x minus 3. And so you might be saying to yourself, well, how in the world are these the same answers? Properties of logs. This negative, doesn't it come up with a log? You can pull it up here as a power. And if I put a -1 on a fraction, what happens to the fraction? It flips, and then you're here. So that's why I think you only really need one formula, because they're the same thing, it's just one of them's flipped over. Who cares? You either use them both or use one of them and pull the negative out. The big thing is what I said. If we have a constant over a quadratic, if we're missing the x term, we've got a formula. All right? We've got a formula. So can you imagine what's coming next? What if we have an x term? Not only that, what if we have a constant over an irreducible quadratic? Irreducible, what does irreducible mean? I can't factor it. So you might be asking yourself, well, what if you can factor it? Stay tuned. It's coming, all right? That's what we're going to do partial fractions on. But if you cannot reduce that, it's not factorable, then complete the square. You get to complete the square. So we're going to look at that denominator and complete its square. So we take x squared plus 2x. We did talk about this last class, right? Yeah. Towards the end. The technique for completing the square, you put it in descending order. You make sure that there is a 1 out here, which there is. If any of you had the pleasure of working through the homework and you got to those, I think you saw me have to pull a constant out, and it's real fun. Here we have a 1, so I'm happy. So I take this, I rewrite it. I take half of that, which is 1, and then I square it, which is still 1, then I add it and subtract it. So I add 1 here and I subtract 1 there. And then I still have plus 17. And then, first 3 guarantee factor to be a perfect square trinomial, which that's fancy language for saying that you can factor it to be that. Okay? And then what's left over here is plus 16. Right? And now we go back over here. Integral 1 over, and this next step I do is really going to test whether or not you're kind of catching on to this common theme that we have. What does that look a lot like? Looks like constant over, yeah, this looks like 1 over u squared plus a squared, right? 1 over u squared plus a squared. In this case, what would u be for us? X plus 1. Now, you have to ask yourself, if I were to let u be x plus 1 right now, would I get any number that pops out that I'd have to scale out later? So what's the coefficient here? 1, right? So the derivative of that is 1. So you're not going to have to scale anything. So you can go straight to the form. What I'm trying to do is avoid doing this. I don't want to have to write down u equals x plus 1. du equals dx. The new integral is 1 over u squared plus 16 du. This is 1 over 4 arctangent of u over 4 plus c. And then plug back in x. I'm trying to avoid that by just thinking about what this is. And I know that that's kind of stretching, okay, but that's what I'm trying to get you all to do, is just stretch out what we've already learned. With the sign, when we had linear in it, right, we had to scale out 1 over a. Cosine, we had to scale out 1 over a. Those other ones we did earlier, we had to scale out by 1 over a. This is a formula, right? But this is linear, so you have to scale out if need be. Okay, well, here's the substitution if you want to go a little slower. X plus 1, derivative of that is dx. Rewrite the integral, it's this. That's formula number 17, right? And then now you go to the, replace the u. So 1/4 arctangent x plus 1 over 4 plus c. Are there any questions on that? Sure? It's your time.
So we just went back to formula 17.
That's 17, yep. This right here. From here to here is formula number 17. Our friend.
So if we have like 2x plus 1, we would have to multiply it by 1/2.
That's exactly right. If this had turned out to be 2x plus 1, then our answer would have been exactly the same as this, but we would have had to have had a 1/2 out there. What if this right here had been negative 3x minus 2? Then I would have had to have scaled out by 1 over negative 3. If you're catching on to that, we have somewhat of a kind of very generic sort of idea here. If we are integrating a function that within it we have a linear function, okay? So this might be 1 over ax plus b. This might be 1 over ax plus b squared. This might be whatever, okay? It is. The antiderivative of this is always going to be 1 over a to compensate for the derivative of that linear expression. And then whatever the hell the antiderivative, capital F, whatever the antiderivative of that function is, right? So whatever the antiderivative of this is, yes, you're going to have it there, but you're also going to have to scale out by 1 over a. That's what's happening here. Do you see that the function we have here is that function, but we have a linear function inside of that function, and therefore we have to try and scale out. So this is a very generic, universal way of thinking about it, but sometimes that's just a little too much for some people to handle. Okay. So we can handle an irreducible quadratic by completing the square and then using a formula. Ah, crap. What if we have a linear expression? This is the first time we've had this. A linear expression over a quadratic. So does everyone understand that if that was just 1 on top, right, then we would probably need to complete the square on the bottom. So long as the bottom didn't factor. So we'd have to check to see if it factors. Does the bottom factor? I don't know how you do it, but I go back to what I have to teach. This is what we teach here is the AC method. So I multiply this number times this number, get 12. I look at the number in front of x, negative 4. I try and come up with two numbers and multiply to be this and add up to be this. And no? So this is an irreducible quadratic. It can't factor. All right? And up top we have a linear. Negative, but that wouldn't have been positive 12. You can't do long division because the degree of the numerator is smaller than the degree of the denominator. So long division isn't going to get you anywhere. You could possibly complete the square here. So let me explain something to you all, okay? When I was a student, all right, I was taught a certain way to do these, all right? And I think the book follows it. No, there are a lot of instructors that do follow the method that I was shown. But as I started to understand calculus a little more, I kind of preferred a different approach. And that's what I like to teach. Now, if you've seen this, I don't know if I came up with this myself. I'm not claiming I did. I just don't remember where I saw it if I did. okay? What I'm getting at is if you go and try and get help tutoring or you ask someone, most people are not going to do it this way, right? But I think it's clever. I think it's a very clever way of attacking this. So check this out. Think about it this way. We have a linear expression on top, right? And we have a quadratic on the bottom. When you take the derivative of a quadratic function, you get a linear function, right? Because the degree of everything comes down. So it would really be nice right now if I took the derivative of the bottom if it was on top. Do you agree? I mean, like, check this out. If I let u be 4x squared minus 4x plus 3, this would be a basic substitution, wouldn't it? And the derivative of this would be 8x minus 4 dx, right? The problem is I don't have 8x minus 4 up here. If that was 8x minus 4, then this would have been a basic substitution and we would have been happy, right? But we're off, right? So I could factor out, what, a 4 here? But even if I factor 4, if I divide both sides by 4 here, I would have 2x minus 1, right? That's not 2x minus 1, that's x minus 1. So you're still off. You see that? And then you couldn't say, well, then I'll divide by 2 because then this would become 1/2, right? So there's no way to turn 8x minus 4 into x minus 1. Do you all agree? There's not an easy algebraic way? Oh, but there is, okay? So check this out. Do we all agree right now that if the numerator looked like this, I'm happy? Yes? Because then we would have 1 over u. And if the numerator was this, that would be du, right? And then the antiderivative would be natural log of absolute value of u. So if the numerator was this, we're in business. Now watch me turn it into that, all right? So let's see if you follow me here. My goal is to make the numerator look like 8x minus 4. So the first thing I'm going to do So can anyone tell me what I did? I multiplied the top by 8, right? I can't do that. That's against the law. You can't multiply by 8, but you can multiply by 8 and divide by 8 at the same time, right? You can do 8 over 8. So if I would have put an 8 over 8 out here, it would be 1, right? And if I pass this 8 through and keep this 1/8 out here, this is right, yes?
Yes.
Okay. That's the first step. I tried to get the 8 first. Now I'm going to get the minus 4. Okay? So what I'm going to do is this. Now I know what you're saying, split up the -8, but just this is the way I prefer to look at it because it won't always work out that nice because sometimes you have fractions. So here's, pardon me?
Where you get the 1/8 from again?
I made it up. I came out here, I took this problem right here and I put an 8 over 8 on the outside, which is 1. So I haven't changed the problem, right? Constants can come out, constants can go in. I chose to only pass the 8 on top through, and I left the 1/8 on the bottom, or I left the 8 on the bottom. Yes? So I'm being clever, right? Okay, so now, I would really like there to be a what there now? A minus 4, right? Minus 4? So I'm going to make my minus 4 appear now. So what I do is I put minus 4. God, dang it. Yeah. Minus 4, right? But I can't just do minus 4. I have to do plus 4 also. There's a hidden 0. But I still have a minus 8 there. Okay. Now, over 4x squared minus 4x plus 3 dx. Are y'all still alive? Okay. Barely? Now check this out. Those two terms right there over that is what I wanted, right?
Yes.
These two come together to be -4, right? And I'm kind of screwed. I kind of fixed it, but then I created a new problem, didn't I? I have this over this, but what's okay with that? This over this is a constant over a quadratic that's irreducible. And then, what? Yeah, we're going to split it up. And this one over here I can handle because I designed it to be handled. This one over here is the previous example, and we're going to have to complete the square on the bottom to do that one. Okay? So now, here's where we are. 1/8 integral 8x minus 4. And then we have, let me write that as minus 4. I think what you were suggesting was that we could have realized that this was minus 4. Yes, I agree, but sometimes this is like minus 1/2. You know? And so instead of trying to figure out what it is, just subtract and add, or like if you needed a plus 4 here, you go plus and minus. Okay, and then you can worry about this stuff later. That make sense? Okay. All right, so I just put those two together, that's it. And then over 4x squared minus 4x plus 3 dx. Now I'm going to split into two integrals. I'm going to do all of this over this, and then that over that, and I'm going to not forget my 1/8 out front, not negative 1/8, 1/8 out front. Any questions? I have not made a substitution, have I? I've done nothing. All I've done is I looked at a substitution that I wish I had, and then I made it happen, created a new issue that I feel comfortable handling. So now here's the new integral. It's actually two integrals. It's 1/8, and then these two terms, 8x minus 4 over the entire thing, 4x squared minus 4x plus 3 dx. And then I have, check me out here, minus 1/2 integral 1 over 4x squared minus 4x plus 3 dx. Understand what I did there? Right, I had this negative 4 was going to be over this, but I pulled the negative 4 out with the 1/8 that was already out there, and that became a negative 1/2. So now I take a step back, I look at this, and I'm like so happy to see this, right? Because this is just 1 over u du by design. That's what it is. So without doing this substitution, without even doing it, I'm just going to go right to the answer. It's 1/8 natural log of 4x squared minus 4x plus 3. Think about what the derivative of this is. It's 1 over this, right? Times the derivative of what's inside, which is that. Minus 1/2. And now we have the pleasure of dealing with this, which is a constant, see, a constant over an irreducible quadratic. We started the problem, it was a linear expression over a quadratic, irreducible. Now we've got it back to this, so we complete the square to do that one. Y'all ready to complete the square? Yeah. Okay. Do y'all have any questions? Y'all are looking at me like this is my fault for some reason. You know, are y'all following this? Yeah. Well, I mean, that's why I record, you know, because you can always go back. Okay. Completing the square on that. Here we go. I need more room. I think I'm going to do it over here. So that means I'm going to erase this part of the answer, but don't forget that's part of our answer. All right. Yeah, it's all gone. All right, just do that right here. Okay, completing the square. Some separate scratch work on the side here. I've got 4x squared minus 4x plus 3. First step for completing the square, got to have a 1 on the x squared. That means I have to factor a 4 out. So 4 comes out, x squared minus 1 plus 3/4, right? When you pull out a number from a number that isn't a common factor, you just have to divide by that number. So that's the same. Okay, then I go complete the square on the inside piece. So I look in here, I have a negative 1. Oh man, I have to take half of that. So negative 1/2,
Yeah.
and then square it. 1/4, I have to add and subtract 1/4. So I have 4 here, x squared minus x. Here I come, I'm going to add a 4th, subtract a 4th. Can you subtract then add?
Yeah.
Nope, you have to do add then subtract. Because when you expand, remember what these first three are going to become? When you expand, that last term always has to be positive because it's the same thing squared. So this always has to be plus then minus. Now earlier, didn't I do minus 4 plus 4? We weren't completing the square. I was trying to make something look a certain way. So I did minus 4 plus 4. Yes, I understand. It's confusing. Plus 3/4. Okay, so there's my hidden 0 in red. The first three are guaranteed to factor. Perfect square. So I'm going to have two sets of parentheses here because I had a 4 and 4 is going to everything here. Then I have these three terms become an x minus a half squared. You know that minus half is actually the first number that you find, always? You know how we take that number, we take half of it? That's always the number that winds up here, always. And then, of course, this is the number squared, add it and subtract it. Okay, so what's still left? I have negative 1/4 plus 3/4, which is 2/4, which is a half. So plus a half, and then like that.
Would you just mention what the number you found first? What do you mean? Number again?
What?
The same word, the one you just told us about, where you have.
When you complete the square, the steps are take out, make that a 1, right? We got that? And then the next step is to look at this number, take half of it. Okay? And then we take that and square it. We add it and subtract it. The first three terms are guaranteed to factor to be x, and then this number right here is always that number you got when you took this and divided by 2. You know how we got negative 1/2? Like, that's not a coincidence. It's that every time. Okay?
It's always going to be x too.
It's always the x in front, and then whatever the number was when you took half of it.
There's always,
And then squared. Don't forget the squared. Okay, so that's what the denominator is, right? That is what the denominator is. Check me out. Negative 1/8. What? Okay, what just happened? Well, that 4 is sitting outside this whole thing, right? So I'm just going to pull it out of the bottom. We're just going to make that a 1/8. Okay? And then I still have on the bottom what? X minus a half squared plus a half dx, right? Questions on that? And if you squint your eyes just enough, that looks like 1 over u squared plus a squared. 1 over u squared plus a squared. And that's linear, right? So I have to compensate for the possible little scaling thing I need to do, but it's a 1 in front of the x, so I don't have to scale. Oh, by the way here, just so we know, what's a? Because I'm going to need it. What's a? Root of 1/2. So root of 1/2, you take the root of the top and the bottom. Root 1 is 1. Root 2 is root 2. So 1 over root 2 is a, right? Okay, I'm going to formula number 17. Going to formula 17. What? Question? Huh?
No, we both thought A was something else.
You got it? Okay. All right, so just this integral is going to be negative 1/8. Formula number 17 tells us that it will be 1 over a, right? 1 over a. That's a. So what's 1 over this? Just root 2. It flips it. So we get just root 2. And then arctan of x minus a half over a, which is this. Were you using the natural log one? No? Yes. Okay, so you're okay with why that's not? Why it's arctan? Okay. That's it, right? Plus c. Well, I still have to paste the other part onto the front, so I'm not quite done. Also, like this, you might like flip this up and just put root 2 here, and then root 2 over 2. Like if you're checking the answer in the back of the book, they're never going to leave it like this. But on a test, this is fine. Like it actually is easier for me to grade because I can tell like there's A, right? And that's 1 over A. So, all right, so final answer is the antiderivative of this is, don't tell me. Don't tell me. Ah, was it 1/8 or negative 1/8? It was 1/8 on that first one? I just couldn't remember if it was positive. It was positive? Damn it. Okay, so it was 1/8 natural log of 4x squared minus 4x plus 3, right? And then this answer right here, which is minus root 2 over 8. I just put those two together. And then arctangent of x minus a half over 1 over root 2 plus some constant of integration. So remember last class when we were doing integrals, trigonometric substitution, and then we would get it to like sine and cosines, and we were like, yes. You know, like, now we can do it, you know? We're going to be happy to see this now. Like on the problems that we do, we're going to be like, ah, yes, it's linear over quadratic. Now I can do it. And this is the way it's done. This is the way I do it. Do y'all like that? I mean, was that okay how I made that weird stuff happen?
Yes, but the fact that you said that we're going to have a bigger problem and then break it up to this and then break it, you know, that's intimidating.
I know it is. I know it is. I know it is. It's pretty sad that this is what you're going to hope to see later, like in a problem, right? You're like hoping to see this so that you can go do this, right? But it's not even hope. It's just kind of like, I don't know.
Wishful thinking.
I'm trying to make an analogy in your life. I don't know.
There's no.
I'm sure you've had problems where, and I'm not going to talk, you know what I'm talking about. Like I'm sure you've gone to work and you've had something that's complicated, but then you realize that it's something that you're okay with, like you're familiar with it, right? And then you're like, okay, I can deal with this. That's kind of what we're going to be like. We're going to be working on a problem. It's like, what the hell? And then you're like, but if I do that, I break it to that, and that I've done before, I feel good, you know? All right. That was number 7. Let's look at number 8. So we theoretically can handle a linear expression over an irreducible quadratic. Theoretically. Now, what if we have an irreducible quadratic over a repeated irreducible quadratic? Oh, wait, sorry, I said that wrong. What if we have a linear expression on top over a repeated irreducible quadratic? So notice x squared plus 1 cannot be factored. So that is a quadratic that's not factorable, it's irreducible, and it's repeated, which means it's squared, right? That could be squared, cubed, whatever. We're going to kind of play the same exact game that we just played. You don't want to play? And that's because this in here, x squared plus 1, if I took its derivative, would give me what? Just 2x. So the question is, can you make your numerator look like 2x? I think so. So I'm thinking here, I would really love my denominator to be u. I would really like my denominator, that to be my u, and then the derivative of that to be 2x dx. The problem is the plus 1, right? The problem is the plus 1. So let's force the numerator to be just 2x and not x plus 1. So what am I going to start with? Multiply 2 on the top, and then 2 on the bottom, so a half on the bottom. So I'm going to do half of this integral is 2x plus 2, right? That 2 has to go through the whole numerator. Now, fortunately for us, all we needed was the numerator to be 2x, right? I can split this into 2 integrals right now. Can't I? So if I split it into 2, I'll have 1/2. I'll have 2x over x squared plus 1 squared dx. That's one integral. The other integral, plus, because this was a plus, is going to be this 2, right? We have the half still. We have the 2 up here and then this thing on the bottom. But I'm going to pull that 2 out. And the half kills it. So I'm left with a 1 here, and then x squared plus 1 squared dx. That seem okay to you? Okay, what happened there is I split this into 2 integrals. I did this over this, plus this over this. So when I do this over this, there it is. I didn't pull the 2 out, and the reason I didn't pull the 2 out is because the derivative of this is that exactly. So I have like 1 over u squared du right there. You see the 2 now on that one? So this one over this, I didn't care about 2 up there, so I pulled the 2 out. All right, can we handle this one now?
Yes.
This looks a lot like integral 1 over u squared, right? Right? And the derivative of it's right up there. So you could work through this one. So I'm going to put a check mark here because we can do that one. What about this one, though? We have a constant over a repeated irreducible quadratic. Have we talked about that? Oh, sorry, I forgot to turn my phone off. Have we talked about how we do a constant over, not repeated, right? We've done a constant over a repeated linear factor, over a quadratic by itself, irreducible quadratic, but not a constant over a repeated irreducible quadratic. Well, if you expand that out, you're going to get 1 over, you're going to have a 4th degree polynomial down here, which you won't be able to do anything with because you can't split it up because all your different terms are in the denominator, not the numerator. So what I'm going to have to do is kind of hit a little quick reset button in my brain and go back to last class and think about this other technique that I also have in my toolbox, which is the trigonometric substitution. And I can rewrite this as the square root of x squared plus 1 I can rewrite this integral as the square root of x squared plus 1 to the 4th power dx. Can't I? Doesn't that, like this to the 2nd power is the same as the square root to the 4th power? And this looks like square root of x squared plus a squared. And the trigonometric substitution for that is x equals a tan theta. Right? That's what it is. I just don't have anything else I can do with this. This is it. I mean, unfortunately, that's what I've got to do. What this? I thought we did that already. Didn't we do that? Did we? We didn't do this? I didn't show y'all this before? Last class? Really? This is the first time I've shown y'all that you can turn something like that into this?
Yeah.
Okay. Oh.
It looked simpler, I think.
Maybe it looks similar. Yeah.
I think it was like.
It was never
I think what it was just, I think it was just like x squared plus 1, and I turned it into this thing squared.
Yeah.
Okay, yeah, so this is the same idea.
Yeah, it's just that it's
Yeah, okay, I get what you're saying. I thought I'd never shown you anything like that before. I've shown you something similar to this. Okay.
it's the same thing.
So that's fair then? No, who cares if it's fair? That's the way it is, right? Right? That's what happens. Okay, well, I guess what you could do is when you're thinking of trig sub, okay? Those main characteristics are a squared plus x squared minus a squared, or a squared minus x squared. Those 3 different things, right? And you need